2 hours later.
Here we go. Oh God! Oh my God, why? Oh, it's so gross, what happened?
I can tell you why. Follow me to the whiteboard. I can tell you why your soda goes flat. It's due to a driving force.
Wait, you mean like driving a car?
No, a concentration gradient. There's more CO2 in the soda than there is in the air, so the CO2 wants to go from the soda to the air. This diffusion can be modeled by Fick's first law, which states that the flux or amount is proportional to the diffusivity coefficient times said concentration gradient. You can plug this Fick's first law into a mass balance, which will give a time-dependent solution to this problem. You can also model this diffusivity coefficient using the Wilk-Chang equation, which is given by this expression here.
I'm not getting any of that.
Oh, we should do a computer simulation to help you understand.
To model soda going flat, we created a new simulation. COMSOL helps to set the general equations in use by letting us choose transport of dilute species as the physics type. Then we can select the study. Because this is a time-dependent simulation, we chose the time-dependent study. Next, we need to set up all of the different structures and materials that we'll be using in the simulation. Going down the materials list, you can choose carbon dioxide, since that's the material we'll be looking at as it diffuses out of the can of soda. Next, we need to create the cylinder, which will act as the container for the soda. To do this, you can set the radius and the height of the cylinder, and once you hit build, it'll just appear on the right part of the screen there. Next, we need to set the diffusion coefficient. We've already calculated this using the Wilks-Chang equation, and we just need to set it here so that we know how quickly, or what the flux is for CO2 out of the can. Now, we need to set the internal concentration for the can. We've calculated this to be about 140 moles per meter cubed. To create the concentration gradient, you also have to set the top surface to the same concentration of that as the atmosphere. To do this, you can just click on the top surface and set it to whatever you want it to be.
We will proceed by adding a mesh to the geometry of the glass. This mesh will determine how many points within the control volume that will be used to calculate the diffusion process. A finer mesh will give more detailed results, but a finer mesh will also increase computational time. After applying a mesh, we will determine the amount of time that we want to run the simulation for. We will choose an amount of time that will give us comparable results with intervals that will give us a reasonable computational time. In this example, we are running the simulation for 7 days. After the setup is complete, we press compute. As you can see, the low concentration colors begin to bleed down the volume of the soda, indicating the diffusion of CO2 out of the soda. As time goes on, more and more CO2 is leaving the container. Our results are 3D concentration profiles that use a color scale to distinguish between high and low concentrations, red being the high concentration of CO2 and blue being a low concentration.
We ran the simulation using 3 different geometries, a glass, bottle, and mug, as well as 3 different temperatures. As you can see, the more exposed surface area and higher the temperature, the more CO2 that leaves the system, as well as leaves it quicker, as shown in the mug, which has a runtime of 1 day, and the bottle and glass, which have runtimes of 7.
Okay, now I get it. So you're telling me that if you decrease the temperature and decrease the exposed surface area, I'm going to get the best soda drinking experience I can.
Yeah, you should know as a chemie to store your soda at the lowest possible temperature and smallest possible exposed surface area. Also, as a chemie, you could work on a refrigeration unit for the said soda, or you could work on insulation in a soda bottle.
All right!
Yeah.